So we're going to take a look at one more example, very similar to the first one, only this is a ski manufacturer wanting to, again, maximize profit. So we're going to start off with looking at the entire problem and figuring out what to assign our variables for. So we've got two different types of skis, downhill and cross country, but we also have two different types of manufacturing, fabricating and finishing. So which ones need to be our variables? If we read a little bit further, the fabricating department has 108 hours of labor to fabricate downhill and cross-country skis, and the finishing department has 24 hours of labor to fabricate downhill and cross-country skis. We're making a profit on the downhill skis and cross-country skis. So I am in the mindset of thinking my variables are going to be downhill and cross-country. All right, so let's take a look. We've got 6 hours to fabricate downhill, 4 hours to fabricate cross-country, and 108 hours of labor to fabricate. So those three pieces of information are going to combine to give me my first inequality. And we have at most 108 hours of labor. We cannot take any more than 108 hours to fabricate the skis that we need. The next piece of information is an hour to finish downhill, an hour to finish cross-country, and 24 hours to finish skis together. So finishing for each has to be less than or equal to 24 hours. And again, we can't have a negative amount of skis. So our axes are going to be constraints as well. And then finally, we need our profit function. So this is how much we are making on each of our skis. So this is our objective function, 40 on the downhill plus 30 on the cross country. All right, so let's graph our feasible region, find those vertices. Again, we're using our axes. I'm not going to regraph those. Finding the intercepts for my red inequality, this is our fabricating department. 108 divided by 6 is 18. I'm going to label downhill for my x-axis and cross country for my y-axis. So 108 divided by 6 gave me my downhill or x-axis intercept. And then 108 divided by 4 is 27 for my y-intercept. And these are all or equal to's, so we have solid lines again. For my green one, both my intercepts are 24. So we have, of course, the less than or equal to, again, gets us shading towards the origin. So we need to figure out where our red and green line intersect in order to get that last vertex. So rewriting this as D is 24 minus C, I'm going to use substitution into my green equation. Plus 4C equals 108. So solving this one quickly, we have C equals 18, which means that D would equal 6. Which is nowhere near where my lines intersect. Good job graphing. All right, so we'll go ahead and set up our objective function. So we have our vertices, our function, and we want to maximize profit. So our vertices 0, 0 is not going to maximize profit. We have 18, 0. We have 6, 18. By the way, here's where I got the 18, 0. Here's another vertex. And then right here, we had an intercept of 24 0, sorry, I had that backwards, that should be 0.24. Alright, so substituting those, and I would assume that fabricating cross country and downhill skis together would maximize profit, but we have to check those other ones, just in case. Our first one would give us a profit of 720. The second one would give us a profit of 780. And our last one would give us a profit of 720. Oops, that's a 0. So again, this making 6 downhill skis and 18 cross-country skis would maximize the profit for this company. Alright, so let's see if you can set up a system of constraints in order to maximize profit.